Last episode, you watched the opposite disaster, a deep sigmoid stack where the gradient at layer 1 decayed to 3 times 10 to the minus 7. The signal starved before it ever reached the early weights. Vanishing is a slow death. Tonight is the loud one. Same depth, same net, but instead of fading, the gradient grows on the way back, doubling layer after layer, until at step 40, the norm hits 10,000. One step that big doesn't nudge your weights, it hurls them off the map, and the very next loss you print is nan. So here's the question for tonight. When one gradient is 10,000 times too big, do you make the learning rate 10,000 times smaller? You'll see why that's the wrong leash and what the right one is. Start with what exploding actually means because the name oversells the drama. Nothing detonates. The gradient is just a vector, and its norm, its length, is what blows up. At init, our norm is healthy, around 1. Then, over 40 steps, it climbs a clean exponential. Each backward pass multiplies the signal by a factor a hair above 1, and 40 multiplications of 1.3 compound into a wall. By step 40, the length is a 1.0i4. Same direction the whole way, only the magnitude ran away. That distinction is the whole episode, because if only the magnitude is broken, you only need to fix the magnitude. Here's the misconception almost everyone reaches for first. The gradient is too big, so my learning rate must be too big. Shrink it. Reasonable and wrong. Look at what your step actually is. Learning rate times gradient. If the gradient norm swings between 1 and 10,000 across training, no single learning rate fits both. Pick one small enough to survive the 1.04 spike, and your healthy steps, the ones where the norm is 1, crawl at 10,000 speed. You'd spend the whole run tuned for the worst frame. The learning rate is a constant knob. The explosion is a moving target. You can't fix a moving problem with a fixed dial. So separate the two things a step carries, a direction and a length. The gradient already points the right way. Descent doesn't suddenly lie just because the vector got long. The only thing wrong is the length. Gradient clipping is the surgical fix. Leave the direction untouched, cap the length. You pick a ceiling, call it clip norm down 1.00, and if the gradient's norm is under it, you don't touch a thing. Only when it punches through the ceiling do you act. That only when needed is why clipping is nearly free. On a healthy run, it does nothing at all. Now the actual operation and the misconception hiding inside it. Clipping just chops each weight's gradient down to 1. No, that would bend the direction because the big components get chopped more than the small ones and the vector tilts. Clip by norm does something cleaner. It computes one scalar, clip norm divided by the current norm at the spike that's 1 over 10,000 and multiplies every component by that same scalar. Uniform rescale. The vector shrinks to length 1 exactly, and because every component shrank by the identical factor, it still points in precisely the same direction. You shortened the arrow, you didn't rotate it. Watch the spike step concretely. Raw norm at step 40, 1.04, ceiling 1.0, scale factor 1.0, 1.04, 1.04. Multiply the whole gradient by that, and the new norm is 1.04x 1.04 1.0, dead on the ceiling, never above. The update that lands is learning rate times a unit length vector, the same modest nudge a healthy step would make. The bomb got diffused into an ordinary step, pointed the right way. That's the line your terminal prints tonight. Raw 1 e plus 04 clipped to 1.0 e plus 0. And the failure you avoid is not subtle, it's terminal in both senses. Without the clip, step 40 applies learning rate times 1.04. The weights leap into a region where the loss overflows the float. You get NF. The next subtraction gives inf of a mod nan, and nan is contagious. It touches every weight, and from there every future loss is nan. There's no recovering. One unclipped step doesn't hurt the run, it ends it. The clipped run, meanwhile, never feels the spike. Its loss is sitting at 0.30 and keeps going. 2 runs, 1 line of difference. One honest caveat so you don't overtrust the leash. Clipping treats the symptom, not always the disease. If your gradients explode because the architecture is genuinely unstable, no normalization, raw, deep stack, clipping keeps you alive, but you're still fighting the network every step. It's a seatbelt, not a suspension upgrade. The real cure for depth instability is structural, and that's exactly where we're headed next. A way to build the network so the gradient can't compound out of control in the first place. Tonight, the leash. Next, the architecture that doesn't need one as hard. Open15 clipping.py. It's one honest experiment. Take a deep net whose gradient norm we force onto a known exploding curve, then run the same 40 steps twice, once raw, once with clip by norm at 1.0, and record both the norms and the losses. No training tricks, no hidden state. The explosion is scripted so the numbers are reproducible and tie exactly to the figure. First, the exploding norm generator. We don't simulate a whole unstable net to get a spike. We model the norm directly because that's the quantity that matters. Raw norm step returns 1.0 at step 0 and grows geometrically to 1.0e4 by step 40, a clean 10-4 step 40 ramp. That's the magenta curve. It's fabricated, but it's the honest shape. Exponential compounding is exactly how real depth-driven explosions grow. Then the clip itself, 4 lines and the heart of the episode. Clip by norm G max norm, reads the current norm, and if it's at or under the ceiling, it returns the gradient untouched. The cheap common case. Otherwise, it computes scale, max norm, and returns G scale. One scalar applied to the whole vector. Note what's not here. No per component logic, no direction math. Uniform rescale is the entire trick. Now the loss models for the 2 runs. Loss clipped step is a healthy decay that flattens at 0.30. The run where every step is a sane unitish nudge. Loss unclipped step tracks it identically until the norm crosses the danger line. The moment a raw step exceeds what the float can absorb, we return float to NaN. And once NaN appears, we propagate it forward. Because that's what actually happens. One NaN poisons every subsequent step. The driver loop runs steps 0 through 40. Each step we compute the raw norm, pass it through clip by norm, and log both alongside the 2 losses. We print every 10th step so the terminal stays readable, and we capture the headline frame, step 40, in full. Raw 1.0 E plus 04, clipped 1 zo plus out, unclipped loss NaN, clipped loss 0.3000 hours. Every printed number is a value the figure will draw. The terminal and the plot are the same data. Finally, we hand the 4 arrays, steps, raw norms, clipped norms, and the loss pair to the plotter. Raw norm goes magenta dashed on a log axis, so the climb to 1.0e4 reads as the straight exponential line it is. Clipped norm goes teal and flat at 1. The loss insets sit in the corner, one diverging to NaN, one holding 0.30. Nothing is computed in the plotter. It only draws what the loop already logged. So the leash works. When the gradient ran to 10,000, we didn't shrink the learning rate and we didn't touch the direction. We capped the length, and the run that would have died at NaN kept descending at 0.30. But remember the caveat, clipping is the seatbelt. Next episode, we install the suspension, residual connections, the identity shortcut that lets the gradient flow straight back through a deep net without compounding, so the explosion never builds in the first place. The leash keeps you alive. The shortcut means you barely need it.